So let us talk about binary search tree, and upon completion of this presentation you'll be able to create and implement binary search tree. In short, we call it as BST, and understand the operation of binary search tree, abstract data type, and write application program using this BST, design and implement a list using a BST, and design and implement threaded trees. So this is the source of this presentation. A binary search tree is a binary tree. Bi means 2 with the following properties: all items in the left subtree are less than the root, and all items on the right are equal to the root. So each subtree is itself a binary search tree. The basic property of BST: in a BST, the left subtree contains key values less than the root, and the right subtree contains key values greater than and also may be equal to the root. So the basic components: binary search tree provides an excellent structure for searching a list, and at the same time for inserting and deleting data into the list. This is how binary search tree is. If this is k, all less than k are on the left side, or greater than or equal to k are on the right side. What are the valid binary search tree? A and B. This A and this is B. This A and B are complete and balanced tree. Look, 6 is less than 17, 19 is greater than 17, and here we have only one node. So they are both complete and balanced tree. If we talk about D, C, D, this is a nearly complete tree and balanced tree. All numbers here, as per the definition, follow the rule. And C and E are neither complete. They are neither complete because you need to have left and right subtree of every node. So C and E are neither complete nor balanced tree, though the numbers are following the rules for BST. These are invalid search tree. See, these are invalid search tree because 22 is greater. Some values are not as per the definition, because 11 is less, and 22 here, see, it is greater than 17. So these are not the valid binary search tree. So I need to talk about this, because on this 6 is lower than 17, but 11 is not lower than 6. Every node has to follow the same ruling. Now BST operations, binary search tree operation, we discuss 4 basic BST operations: traversal, search, insert and delete, and develop algorithms for searches, insertion and deletion. So traversal, searches, insertion, deletion. Binary trees traversal. First, traversal. Traversal means traveling from where to where we are going. The source and the destination is what it decides, that what order do you traverse. So this is pre-order traversal. This is tree order. So this is like this. Okay, I'll tell you more about this. In order traversal is like this, because we first go here 1, then 2, then 3. The node is basically which decides. Now here on this post order, we take left subtree, then right subtree, and then the node. And here in pre-order, first we take node, then left subtree, and then right subtree. So example of binary search tree, a complete binary search tree is like this, right? All numbers or all values, key values on the left hand side, left subtree is less than, and rather if we consider this, it has to be in the same accordance with the ruling. This is the pre-order traversal, as I mentioned earlier. So how to traverse pre-orderly? First of all, you have to go to the node, right? 23. Then again on the left subtree, again you have to go to the node 18, then left subtree 12, and then the right subtree, right? So 18, 12, 20. Now this is complete. because this is node, this is left subtree. Left subtree has to be reiteration, means the same rule has to be applied here, and then this node, left subtree, and then go to right subtree. Right subtree again follow the same ruling, first the node, then the left subtree, and then the right subtree. So 44, 35 and 52, these are the numbers which show that this tree has been traversed pre-orderly. Then post order, what you do in post order? First of all, we take this left subtree. So again left subtree, first 12, 20 and 18. The post means the node has to be traverse in the latter part, means you need to travel the left subtree, then right subtree, and finally in the end the node. So 12, 20 and 18. Then let's go to the right subtree, again follow the same ruling, 35, 52 and 44, and once this is done you can go to 23. This is the post order traversal. Now in order traversal, how does in order travel takes place? In this, in order means the node has to be in between. So let's see, first left subtree, then node, and then this, then means the central node, the root primary node. So let's take left subtree, first 12, then 18, then 20, because this has to be in between. Alright, then go to this, and what we are going to compute? First this number 23, 12, 18 and this 18 we have computed, but this left subtree will be followed by this root, and then we'll go to this place, because in order means this has to be in between. So see, 23 is in between. Now let's go to right subtree, 35, then 44, 52. This is the in order traversal. So in order traversal of a binary search tree produces a sequence list. Now you can very well perceive that when we traverse in orderly, the numbers are automatically in ascending order. Now right node left traversal, right node left traversal. So 52, right, 44, then 35, then we go to 23, then again we come to right node, 20, then 18, then 12. Okay, this because we are, if we take this as one node, this as one node, we will go from here, first this one, this and this. Okay, first take the right node, then the center node, then the left node, but in this we have to follow the same rule. So we take 52, 44, 35, then go to 23, then 20, 18, 12. Right node left traversal of binary search tree produces a descending sequence. Okay, the in order produced the ascending order, and the right node left traversal produced the descending sequence. Now 3 BST search algorithms, binary search tree search algorithm, is find the smallest node, find the largest node, and find a requested node. So this is a algorithm for finding the smallest node in a BST. So finding smallest node, this algorithm finds the smallest node in the BST. So this root is pointed to a non-empty BST, binary search tree or subtree, then return address of small node, right? Now if left subtree is empty, return root. Okay, and if this is done, return find smallest BST, left subtree, and find smallest BST. So this is our function name, find smallest BST, and this is done again and again. And if we see left subtree is empty, then we return root, otherwise we compute it again and again. Let me show you. The find the smallest node in a BST. This is left subtree not empty, because if it is empty, it will be the final number 23 will be returned, but now this is not empty. We go here, right, we go to the next node, left subtree. Left subtree is again not empty, then we go to left subtree. This is either empty or not empty, but this is non-empty. You don't have a left tree or right tree. So this 12 will be returned. Okay, now you understood what has been said here. Now largest node, again the largest node we follow the same thing. The algorithm finds the largest node in the BST. Pre-root is a pointer to a non-empty BST or subtree. Return address of largest node return. So if right subtree is empty, return root. Otherwise follow the same ruling, right? Let me explain to you. Now we just saw how to find the smallest node, and in the similar fashion we can find the largest node, because in this you are going from node to the leftmost subtree, and in the similar fashion you have to go to the rightmost subtree until you don't find any root left tree or subtree. Means if it is empty, means it has no left or right subparts, you can very well find out that this number will be the highest. So this is what this has been shown here. I hope you'll do it. And let us go to BST and the binary search. Now we have certain number. We have 12, 18, 20 and 23, then 35 and 44, 52. These search points are in binary search tree. We make it as a binary search tree, and then let us see what we have to do. So this is the algorithm. If we have to find the target key, means the number which needs to be found. So searching a binary tree for a given value, the root is the root to a binary tree or a subtree. Target key is the key value requested, and return the node address if the value is found, null if the node is not of the tree. So if empty tree, you don't have the number, return null. But if target key is less than root, this is very important. If target tree, the number which has to be found is less than root, what you have to do? You have to go to the left subtree, and in otherwise case, means if target key is greater than root, you go to the right subtree. You compute it again and again. You find it out, and number or the value is found. You end the search. So let us see how it has been done. Now if you have certain number, say the target is less than root, go to left, and target is greater than root, go to right, and this is 20. If we need to find out 20, this is how we have to go. See, let me show you. If I have to find 20, I will go here. 23, 20 is greater than 23 or less than 23? 20 is less than 23. 20 is less than 23. So we take the left subtree. This node we need to for greater than and less than, we have to find for the key value. Now the 20 has to be found, whether 20 is greater than 18 or less than 18. 20 is greater than 18. So now we don't go to the left subtree, we go to the right subtree, and this is where the value will be found. So the complexity or the number of searching reduces drastically. This is the most important aspect of our BST searching. Now BST insertion, to insert value, all we need to do is to follow the branches to an empty subtree and then insert the new value. Okay, and in other words, all insert take place at a leaf or at a leaf-like node, a node that has only one null subtree. So this is we have the numbers which generally we have taken in earlier slide. Now after, you need to insert 19. Okay, what before, this is before inserting 19. Now what after inserting 19? You can insert 19 here, because 19 is less than 20, right? And this is before inserting 38, which is greater than 35. So we have to insert it here. This is how inserting can be done. Inserting needs to, let me retell you that the number will be inserted only at this node, the node which is called the leaf, and where we have only one subtree, or either on the leaf or only on the node where only one tree is there, I mean left subtree or right subtree. Okay, so we can put it here or here, wherever, but when we are putting 38, we need to put it on the right hand side, this on the left hand side, because 19 is less than 20 and 38 is greater than 35. Now adding a node to BST, that again, if empty tree is there, set the root to the new node, means if there is no tree, set it as a root, otherwise new node. This is how done. And this is that if new node is less than root, then we have to go to the left subtree and then put the new node. If we have this condition not met, then we go to the right subtree and put the new node. Okay, this is 19, a new node. Now this new node is less than root. Where we have to go? Certainly we have to go on the left. Now check for 12. New node 19, new node is greater than root. So where we have to go? Because 19 has to be put. Go to the right subtree, means you need to place 19 on the right, because this, you have a space here, you have a right subtree, you are having a place to put this as a right subtree, and this will also not imbalance this tree, so we can place it here. And now the deletion, there are following possible cases when we delete a node. The node to be deleted has no children. In this case, all we need to do is to delete the node, one node. And the node to be deleted has only a right subtree. So we delete the node and attach the right subtree to the deleted node's parent. Okay, the node to be deleted has only, if it has only a right subtree, we delete the node and attach the right subtree to the deleted node's parent. And the node to be deleted, if it has only a left subtree, we delete the node and attach the left subtree. The node to be deleted has two subtree. If it has two subtree, it is possible to delete a node from the middle of the tree, but the result tends to create a very unbalanced tree. So deletion from the middle of a tree, rather than simply deleting the node, we try to maintain the existing structure as much as possible, finding data to take the place of the deleted data. This can be done in one of the two ways. Deletion from the middle of a tree, the first is we can find the largest node in the deleted node's left subtree and move its data to replace the deleted node's data, or we can find the smallest node on the deleted node's right subtree and move its data to replace the deleted node's data, right? And either of these moves preserves the integrity of the binary search tree. This is how deletion is done. If we want to delete, if it is less than root, we delete, again go to delete and left subtree, we delete the key, and if it is greater than root, then we again delete by deleting this from the right subtree. So if delete not found, test for the leaf node. Okay, and if no left subtree, make right subtree the root and return true. This is all 1 1 1 1 1. Okay, here you have to place it, but let me show you, because there are other also. So if no subtree is there, make left subtree the root and return true. Else, node to be deleted, not a leaf, find largest node on the left subtree, save the root in the delete node, set largest to largest BST left subtree and move data in largest to delete node and return delete BST. So okay, let me show it to you now, deleting the BST test cases, because once you understand that, you will understand the algorithm as well. Now I have to delete this 23. Node to be deleted is 23. What to do is, now if I have to delete this 23, the largest key on the left subtree, the largest key on the left subtree is what? This is 22. So what I have to do is I will delete this 23, but what I have to do is I have to place this 22 here, right? So we have deleted the largest node, and the largest node deleted is, because we have to delete 23, and if I want to delete 23, I just can't, keep these left or right hanging. if I don't want to keep it, what I have to do, I have to take the largest from the left subtree, and the largest can be placed here. Okay, so I hope you understood how